A continuous game is a mathematical generalization, used in game theory. It extends the notion of a discrete game, where the players choose from a finite set of pure strategies. The continuous game concept allows games to include more general sets of pure strategies, which may be uncountably infinite. In general, a game with uncountably infinite strategy sets will not necessarily have a Nash equilibrium solution. If, however, the strategy sets are required to be compact and the utility functions continuous, then a Nash equilibrium will be guaranteed. This is by Glicksberg's generalization of the Kakutani fixed-point theorem. The class of continuous games is for this reason usually defined and studied as a subset of the larger class of infinite games in which the strategy sets are compact and the utility functions continuous. Formal definition. Define the n-player continuous game where is the set of players, where each is a compact metric space corresponding to the th players' set of pure strategies, whereas the utility function of player we define to be the set of Borel probability measures on, giving us the mixed strategy space of player I. Define the strategy profile where let be a strategy profile of all players except for player. As with discrete games, we can define a best response correspondence for player is a relation from the set of all probability distributions over opponent player profiles to a set of player S strategies, such that each element of is a best response to. Define. A strategy profile is a Nash equilibrium if and only if the existence of a Nash equilibrium for any continuous game with continuous utility functions can be proven using Irving Glicksberg's generalization of the Kakutani fixed-point theorem. In general, there may not be a solution if we allow strategy spaces S which are not compact, or if we allow non-continuous utility functions. Separable games. A separable game is a continuous game where, for any I, the utility function can be expressed in the sum of products form, where, and the functions are continuous. A polynomial game is a separable game where each is a compact interval on and each utility function can be written as a multivariate polynomial. In general, mixed Nash equilibria of separable games are easier to compute than non-separable games as implied by the following theorem. For any separable game there exists at least one Nash equilibrium where player I mixes at most pure strategies, whereas an equilibrium strategy for a non-separable game may require an uncountably infinite support. A separable game is guaranteed to have at least one Nash equilibrium with finitely supported mixed strategies. Examples. Separable games. A polynomial game. Consider a zero-sum two-player game between players x and y, with denote elements of and as and respectively. Define the utility functions where the pure strategy best response relations are, and do not intersect, so there is no pure strategy Nash equilibrium. However, there should be a mixed strategy equilibrium. To find it, express the expected value as a linear combination of the first and second moments of the probability distributions of x and y. The constraints on and are given by Hausdorffers. Each pair of constraints defines a compact convex subset in the plane. Since is linear, any extrema with respect to a player's first two moments will lie on the boundary of this subset. Player I's equilibrium strategy will lie on. Note that the first equation only permits mixtures of 0 and 1, whereas the second equation only permits pure strategies. Moreover, if the best response at a certain point a player I lies on, it will lie on the Helmholtz line, so that both 0 and 1 are a best response. Simply gives the pure strategy, so will never give both 0 and 1. However, gives both 0 and 1 when y equals 1/2. A Nash equilibrium exists when this determines one unique equilibrium where player x plays a random mixture of 0 for 1/2 of the time and 1 the other 1/2 of the time. Player y plays the pure strategy of 1/2. The value of the game is 1/4. Non-separable games. A rational payoff function. Consider a zero-sum two-player game between players x and y, with denote elements of an is and respectively. Define the utility functions where this game has no pure strategy Nash equilibrium. It can be shown that a unique mixed strategy Nash equilibrium exists with the following pair of probability density functions. The value of the game is, requiring a Cantor distribution, consider a zero-sum two-player game between players X and Y, with, denote elements of an is and respectively. Define the utility functions where this game has a unique mixed strategy equilibrium where each player plays a mixed strategy with the Cantor singular function as the cumulative distribution function.